All right, I hope it's recording now, but I think the red dot here means that I'm recording. All right, so just like in addition to what we talked about 2 weeks ago, right, when we were talking about interval versus point estimates, and I didn't quite cover so the last slides where what I was planning to talk about the relationship between interval estimation hypothesis testing. So there's a pretty close relationship. And I just wanted to make sure that it's all clear to you, so that it's clear to all of you. All right, so the major difference actually between interval estimations, so the estimation of confidence intervals, and hypothesis testing is that when we use interval estimations, we do not need to begin with an a priori belief about the population parameter of interest. So in case of means, so we don't have to actually have a hypothesis about what we think the mean, the true mean in our population is, right? So that is not necessary. So for determining a confidence, or for calculating a confidence interval, however, it is a starting point for each hypothesis test, right? So about the mean. So we have to have a hypothesis, and then we collect data. So we draw our sample, and then we make a decision on how likely, how probable, so this sample is given, or the statistic that we calculate from the sample, right? Our sample mean given this assumed population parameter. So it's a different in the logic, so the ideas that we start with, but the mathematical calculations are actually quite similar. So we are using the same sampling distribution, right, for the confidence interval, and also for our hypothesis test. And if you remember, so this flashlight example that we were talking about, right? So company has developed a new flashlight. And then in class, so 2 weeks ago, we were calculating so the 95 and 99% confidence interval for the life. So basically how long these new flashlight batteries live. And so now let's change the focus a little bit and so make that a hypothesis test. So now rather than coming up with an interval estimation of the battery life, we actually want to test a specific hypothesis about the battery life. And so let's just assume that our hypothesis is that the new average life for the flashlight is 151 hours. Right? And so then you may recall that the sample mean, so for our flashlight sample was 150 hours. So we had 100 flashlights in that sample. And our population mean was, as a population standard deviation, was 4 hours. Oops. Let me, okay, I think I don't see the, so if I'm actually in presenter mode, I don't see the, wait a second, let me put that somewhere else. It's always difficult to see the chat. So if you're asking questions, so it's actually better. So if you have any questions, so just unmute yourself and ask. So because it's difficult for me to track the chat while I'm talking. All right. So what is the relationship, right, between our interval estimations and hypothesis testing? So obviously, if we consider the values that are in our, let's say, 95% confidence interval, right? So where, of course, now we have to calculate that as 1 minus alpha. So alpha is a significance, so the significance level for our significance test, right? So if you basically want, if you're looking at the 95% confidence intervals and then looking at a significance level for the hypothesis test of 5%. So then, so the values within that confidence interval, right, within that 95% confidence interval, those would be considered plausible mean values if our null hypothesis was right. Yeah. So everything that's in this interval, right? So we would consider that a plausible value under the null. So basically for the null hypothesis. Yeah, so if our null, basically, so that would lead to the reverse conclusion that values that are not in this confidence interval are not considered plausible as null hypothesis values. Well, that means if the value right? So if our assumed null hypothesis value is not within the limits of the confidence interval, then it's probably not compatible with the idea that this is basically that the flashlights come from a population with a true mean that corresponds to that null hypothesis value, right? Okay, so that means we may reject or not reject a given null hypothesis in favor of an alternative hypothesis, depending on whether the confidence interval includes our null hypothesis value or does not. Yeah, so again, so those values that are within the confidence interval, those are values that are plausible under the, so as null hypothesis values, whereas values that are outside the confidence intervals are not plausible, yeah, as a null hypothesis value. That means if our confidence interval, so that we have calculated, if that does not cover 100, if it does not include the 151, then basically, so then it does not include a value that is basically, that this 151 is not a plausible value, right? As a true population parameter for our sample, so underlying our sample. Okay. And that was a case, right? So our 95% confidence interval, so that was 149 to 1, so something to 150 point something. So that did not contain the null hypothesis value of 151. And therefore we can conclude that the null hypothesis, yeah, so that the true population mean is 151 is not plausible. Yeah? We reject it in favor of the alternative hypothesis that the true mean is different from 151. And we can further conclude, right, that the true population mean that probably the flashlights come from a population where the true population mean is lower than 151, right? Because our confidence intervals, our interval estimate was a value lower than the assumed value of 151. So as I said, so and the crucial difference or the logic of all hypothesis testing, so we always assume that the null hypothesis is true. Yeah, so we always assume that the underlying logic, we assume our null hypothesis is true. So in this case, for this example, we assume the 151 hours are the true life of the new flashlight batteries. And then we use a sampling distribution of means in order to determine how probable, yeah, so how probable it is to get a sample mean like the one that we observed under the condition that this null hypothesis is true, right? So we know, so the sample, we know what the sampling distribution looks like for a population that has a true mean of 151. Yeah, we know exactly what it looks like, right? We know the parameters, we know the mean, that's 151, and we know the standard deviation, which is a standard error. Right? Depends, of course, on our sample size. And then we compare the sample mean with a known distribution, right, under the null hypothesis. And if our sample mean, our observed sample mean, is an unlikely event, and for this sampling distribution, then we reject the null hypothesis. So that is basically make sure that you understand, because that's the logic. It's the easiest case, right? But that is the logic of all significance tests and statistics, right? So this most simple model. So we assume some null hypothesis. We assume it's true. And then we say, what is a sampling distribution under the assumption that the null hypothesis is true? Then we take our sample mean, so the observed sample mean, and we say, is that a probable outcome? Is that a probable statistic that we obtain if we draw from a population that has this true mean? Yes or no? Yeah, and if it's in the tails of the sampling distribution, if it's an unlikely event, then, right, if basically it's under the significance levels that we determined a priori for this test. Yeah, if it's like in less of 5% of the cases or less than 1% of the cases that we that we would get such a sample mean, then we're inclined to say we reject the null hypothesis in favor of our alternative hypothesis. Well, that is the underlying logic. So here you basically just see a histogram to show that so that same idea, just to make it a little bit more, yeah, to show you like a graphical display. So so we know from the center limit theorem that our sampling distribution is approximately normal, right? So our sample size is large enough, so we know it's an approximately normal sampling distribution. And so if our, right, and that is the sampling distribution under the hypothesis, under the assumption that our sample comes from a population that has a true mean of 151. And in this case, it is centered on the 151, right? So it's centered on the population mean. And we also know what the standard deviation of this sampling distribution is. We know what the standard error is. Yes, it's just the population standard deviation divided by the square root of our sample size. And so here, right, this so these two tails here, so the red shaded areas here in the sampling distribution, so they basically represent the probability of obtaining a sample mean by chance that is more extreme than the actual sample mean that we have observed in either direction.
It's not that easy, but
sorry, was that a question? Okay. So yeah, so these two tails here of our sampling distribution. So they basically tell us, so the area under the curve here, so it represents a probability to obtain a sample mean that is as extreme or more extreme than, in this case, 150 or 152, right? So to get a sample mean that is less than 150 or more than 152, if the true underlying population mean is 151. Yeah, and we would say that is highly unlikely. And that's why if we obtain a sample mean that is 150 or lower, or that is 152 or higher, we conclude, we infer that this sample probably does not come from this population. Yeah, so we reject the null hypothesis. And so I mentioned that last week on Thursday already, but I just want to reiterate because not all of you were in the meeting. So this idea is that we just discussed, right? So this logic, that is nothing but a z-test. So that is known as a z-test, and a z-test is the brother of a t-test, right? The one sample z-test, brother of the one sample t-test. And a z-test is very much the same as a t-test. It is just the test that we're using if the population standard deviation is known, right? So if we know the population standard deviation, if we don't have to estimate the population standard deviation from our sample, then we can use the standard normal distribution to calculate the or to determine the sampling distribution of the mean. If we do not know the population standard deviation, if we have to estimate it from our sample based on the formulas that we were discussing last week, then we have to use the t-distribution for our inferences, right? Which is very similar to the standard normal distribution, to the z-distribution. It's just a little has better tails, right? And it depends on how many subjects we have in our sample. So it depends on the sample size, and this increasing sample size is approximating the standard normal distribution. So it gets more and more similar. Yeah, and so this is just a reminder, you should know all of that. Yeah, so what basically the formula, so the test statistic for this z-test is, it's just the sample mean, right? So we are basically calculating the difference between the sample mean, the deviation of our sample mean from the assumed population mean, and we are dividing by the standard error. So that means by the standard deviation of the sampling distribution of the mean. And so in this case, right, would be 150 minus 151 divided by, that is a standard population. There's a standard deviation in the population, that is our sample size here. And that will lead to a z value of minus 2.5. Yeah, and the area under the normal curve to the left of minus 2.5 and to the right of 2.5 equals 0.024. Yeah, that's the p-value for this test. So that means, so 1.24% of the basically all values under the standard normal distributions are more extreme than minus 2.4 or plus 2.4. So, yeah. That means, yeah, so just to make the connection to our example again, if the true battery life was 151 hours, then again, right? So 1.24% of all random samples of size 100 would have a mean of less than 150 hours, and another 1.24% would have a mean life of more than 152 hours. All right, so that's actually just a summary that I did not want to reiterate. I just want to make that point and remind you of the logic that underlies each significance test. Okay, so then let's talk about so this week's topic. And so let me actually close that here. Okay. I assume you're seeing the presenter view again. Is that correct?
That is true.
All right. I will just make it very small. I keep it that way so that it's basically not too disturbing for you. I keep it that way just so that I don't forget to say things that are important, right? So sometimes I have certain aspects in my comments that I would like to mention. I just want to make sure that I cover that. Okay. So as I said, so today I wanted to talk about data screening and about exploring assumptions. And that is a topic that is very, very important. It's often neglected in statistics classes, but it's really crucial. It's also often not tested. So assumptions, so test assumptions are often not tested in, in real life. So many people don't care, many researchers even don't care much about it. And that's a big problem. And that's why I put a lot of emphasis on it. And we will come back. So each specific test, each specific statistical test that we're talking about, so we will talk about the assumptions and what we need to check before we actually run this, or before we actually use that statistical test, right? And whether we might work with alternatives if the assumptions are violated. So before we are talking about assumptions, it's also important to differentiate between parametric and non-parametric statistics. So it's a little bit a misnomer because it is not, so it is, it somehow implies that non-parametric statistical tests so do not make any assumptions about parameters at all. It is not true. They just make fewer assumptions. And so we will talk about that when we talk about the specific tests. But so in general, we have to worry about assumptions when we're working with parametric tests. And those parametric tests are the most commonly used ones. Yes, it's a t-test, it's a regression analysis, it's an analysis of variance, right? These are all a correlation, right? So as a Pearson correlation, these are all, Pearson correlation itself is not a test, but so the significant, so the t-test or the z-test that analyze, so that's used to make inferences about the correlation coefficient is a parametric test. So these are all parametric tests, right? And so they're associated with certain assumptions. And so first of all, I wanted to define, so make clear what is meant by parametric statistics. So parametric statistics basically assume that your variables of interest come from a population that can be described by a known probability distribution. And it's important that this probability distribution can be fully defined by a fixed set of parameters. So a prototypical example is a normal distribution. So normal distribution is fully specified by two parameters, by the mean and by the standard deviation. So if I know mean and standard deviation, then I know exactly what my normal distribution looks like. So that is all I need to know. So, and if we use that knowledge about the parameters of a population distribution in conducting a hypothesis test about a variable, then we're using a parametric test. So that is the main defining feature of a parametric test. So we're assuming that our variables of interest come from a population that can be described by a known probability distribution. So we're making, and that is also the reason why the counterpart of parametric statistics and non-parametric statistics are often called distribution-free, because they do not make assumptions about the probability distribution of the variables of interest. And so non-parametric tests, they don't require the typical assumptions that parametric tests make. And therefore, they're more versatile. So they can be used if those assumptions are not met. It comes with certain disadvantages that we will talk about in a second, but so it's always important to keep that in mind. So, I mean, I mentioned that, right? So our most famous tests that you're also already familiar with. So these are all parametric tests. So they all make assumptions about the probability distribution. So of your variables, of our variables of interest. In many cases, it's a normal distribution, but it does not have to be a normal distribution, right? So, and they're used if the dependent variable is at least interval scale. It can also be ratio scale, of course, but it has to be at least interval scale. Non-parametric tests are more robust, right? So they, in the sense that they do not require these assumptions. So we don't have to make any assumptions. So it does not matter, for example, if a variable is of interest comes from a non-normal population distribution, or has a non-normal population distribution, right? So that is irrelevant for non-parametric tests. But in many cases, they're also less powerful. That means you need larger samples to find an effect of the same size. So that's why so we want to use a parametric test if we can. So because it has more power. So, and in statistics, in our or when we are using statistics, right, in our practical use of statistical tests, so the question whether we can use a parametric or non-parametric, or a parametric test, or whether we need to use a non-parametric test. So we most frequently have to ask that question when we have a very small sample, because for very small samples, we cannot rely on the central limit theorem. So we cannot rely on so this knowledge or this assumption that or sampling distribution will be approximately normal. And so that can come with serious consequences, right? So if the basically the distribution of our variables in a small sample does not comply, is not basically what is required by the assumptions of this test, so then so our inferences are also not valid. And I mean, the first point is more of theoretical nature. When you at some point work with more sophisticated tests, it should not be relevant. So for this class, so if we basically know that our data comes from a known population distribution, but we know that this population distribution violates the assumptions of the central limit theorem, then we also have to use non-parametric tests. But it's a very specific case. And so most of the time we will have to wonder about assumptions when we have small samples. Okay. So I mentioned that before, right? So we should really worry about assumptions, because when they are violated, our resulting statistics, so the results and our conclusions will not be valid. And so particularly common assumptions when it comes to parametric tests are so the normal distribution of our data, or actually in most cases of the residuals. We will talk about that in a second, right? What I mean by residuals is that so the residuals or error terms are normal. So yeah, but basically what remains unexplained after the model has been applied. So in our data, so these residuals, these error terms have to be normally distributed. And the second very, very common assumption is that so the variances are homogeneous, so that we have equal variances. So you might know that from the independent sample t-test, right? So where one of the assumptions is that so the variance of your variable of interest, of the dependent variable in both groups that you're comparing has to be the same, right? And so you also probably know that from the analysis of variance, where also the variance of your dependent variable in all your groups has to be identical. And the same is true for regression analysis or correlation. So where it's more commonly referred to as homoscedasticity, but it's basically also just the assumption of homogeneity of variance. So it simply means that the variance of your dependent variable is equal, is constant across all levels of your predictor, yeah, across all levels of the independent variable. So if you have a regression model, right, you have one predictor. Let's say you want to predict the height from weight. Right, you build a regression model, so where you have like a certain, right, you have a linear relationship, and you build this model or estimate the model where you want to predict weight from height. Then so basically for each possible value of height, the variability of your data points around the regression line, so around the predicted values, has to be the same. Yeah, the standard deviations or the variance of these residuals of the error term has to be constant across all values of your predictor. And that is nothing, so right, it is no different for an analysis of variance where you have the different groups, except for that you have a categorical predictor here. So same idea. Also, that is not really an assumption. It's just something that is very important and always needs to be checked. So parametric tests are very sensitive to outliers. Right? So outliers might bias our, might severely bias our findings and might lead to invalid conclusions. So we always have to check for the presence of outliers. And so that is something that I just wanted to highlight, of course. So that is true for any statistical test. So for both parametric and non-parametric tests, or any statistical test that you ever perform and run. So they all require random sampling. You have to have a random sample, and your observations have to be independent. Okay. So, but Yeah, random sampling, right? We were talking about that. So so the data in your that you capture in your samples, the data in your sample, your subjects, your observation units, they are randomly chosen from your target population, from your population of interest as a whole. And the sample, so any sampling bias that we might introduce, right, by having like a non-random sample, will affect external validity of the outcome of the analysis. Yeah, that means the generalizability of our findings, so whether we can generalize beyond our sample or not. Right. So if our sample is not random, then worst case scenario, the conclusions, our results of our analysis are only valid for this particular sample, nothing else. So it's also important to keep in mind that there is no post hoc test for random sampling. So you cannot tell whether it's a random sampling after you've collected your data. So you have to make sure that you choose the right sampling method to meet that requirement. So in addition to random sampling, all statistical tests assume that the observations are independent of one another, except when the analysis explicitly takes this non-independence into account. So what does it mean? So often we have something that is called a dependent samples analysis, yeah, or within subjects design. Right, so that means that we are repeatedly observing the same observation units or the same subjects. So that could be that, for example, we're interested in so post-test, pre-test, post-test comparisons, right? So we have some intervention, so that is supposed to like some some new drug, yeah. So it's supposed to improve blood pressure, and then we measure blood pressure before. So people use the drugs and blood pressure after. Because I mean, let's not talk about control groups or whatever right now. Just let's focus on this pre-post measure, right? So and then if we wanted to compare so our pre and post blood pressure scores, of course. So the observations for the same patients, for the same participants, would be dependent, right? So they're not independent. They come from the same person. So and so that is meant, right? So whenever we have a matched sample, right? So if participants or observation units are matched based on certain characteristics, which we often do, right? So also, let's stay within the same topic. So drug evaluation studies. So we often right? So let's say we have a new drug, and then we compare this drug in a certain patient group and then in a control group. So then we want to make sure that we have no systematic difference between our control group and the experimental group, right? So let's say the control group gets a placebo. And what is often done is that so the participants are matched. So for example, based on age, based on their certain comorbidities, et cetera, right? So that each subject, each participant in one group, so in the experimental group, is basically matched to one participant in the control group based on these characteristics, so that they're as similar as possible. So when we are right, so when we're randomly assigning our participants to control group versus experimental group, and in this case, so there's also a systematic relationship, right, between these paired observations, so they're not independent from each other. Yeah, so that means we always have to use a statistical test for dependent samples that accounts for that, right? Or when we examine siblings or spouses, right? So when we have like pairs of observation units of subjects that are related to each other. Okay, so but even if we have a repeated measures experiment, a repeated measures design, so still we assume that the observations from different subjects are independent. So, and when I say different subjects, then I mean those that are not matched to each other, right? So that is the idea. So when we are, it's always like one of my favorite examples. If I, for example, was interested in testing whether so the exam scores are better among this class, so the mean exam scores in this class are better than some, I don't know, imaginary parallel section of this course that might be taught somewhere else, then I have to make sure that, so for example, student A is not copying the answers from student B, who happens to sit next to student A. Yeah, so because then I have a non-independence of observations. Yeah, so then the results, my exam scores for student A and for student B will be related. Yeah, so they will be correlated. So, and that is what is meant by independent observations. Yeah, so the values for different observation units are independent from each other, if you take into account that we might have dependent samples, right? And then of course it's not true for those pairs of observations, where the model takes that explicitly into account. And similar to so the idea of random sampling, or the assumption of random sampling, so our independence of observation is assumed from good experimental design. Yeah, so there's no way, or almost never, it's not true no way, but there's almost never a way to determine whether your observations are independent after you have collected the data. So basically, from just looking at your data, cannot tell whether they're independent or not. Either they are or they're not. Yeah? Either your design has made sure, either you have made sure that student A cannot copy from student B, or you have not. But later you can tell. It's not possible. In some cases, though, there is some natural order. Yeah, and then you can plot the data or residuals in that natural order to see if the observations from one date are correlated to those from other dates. So often you have some trend. So you could, for example, if you have tested or collected your data in a certain order, right? So if in a temporal order. So then you could check whether you see an effect of that. So basically, you could bring your observations or your data in that temporal order. You can check whether you see some trend, right? Whether there is some temporal autocorrelation between consecutive time points, or if you have some spatial, right? Like in our classroom or test score, exam score example, you could check whether the setup of the classroom, right? So who sits next to whom, whether that has any, whether there's like a notice, so a pattern that can be noted from the spatial arrangement of so the classroom layout, so who was sitting next to whom. But in most cases, you don't have that information available, and then there's no way for you to test that. So here, that is the rare case where you have, as I said, so some natural order of your basically of your cases, and so right. So for example, if you know that you basically obtain the first data point on day one and the second one on day two, etc., right? So then you can bring them in the temporal in this order here. And here you would see data that have no temporal correlation. So that means, yeah, so the data point, so a given data point does not depend on basically what the value of the preceding data point. So there's no systematic correlation. So that means it does not matter whether this one is a higher or lower point, right? So so it does not influence the value of the subsequent data point. So it could still be high or low, right? And here you see a systematic patterns on autocorrelation. So that means that if the preceding data point had a smaller value, then the following data points are also more likely to have a smaller value, and so vice versa, right? So you see that they're basically, so that, that they go from small to large here over time. That means there's a positive autocorrelation. So smaller, so it's closer to the predecessor. So the a particular value. All right. Just a reminder, right? So parametric tests assume that the data come from a population that has a known distribution, right? And can be described as a relatively small set of parameters. So in particular, many tests that we will discuss assume that the data are normally distributed once the effects of the variables in the model are taken into account. So, and that means nothing but the residuals are normally distributed. Residuals from our analysis or residuals from a model are also commonly referred to as errors, right? So errors, residuals, same thing, you know? And so an error is nothing but the difference between the observations and the value that is predicted by our model. So that is all sounds a little bit abstract, right? So let's make it a bit more concrete. Yeah, so for example, let's assume we calculated the mean of a sample and that mean is 10. Then we might have one observation that has a value 12 and we have another observation with value 7. So then the residual for the observation that has a value 12 would be 2, right? So it's just the difference between the mean, which is in this case a model, right? So mean is our model. And so the difference between the model prediction and our observation would be 2, right? So 12 minus 10. And for the other observation that has the value of 7, our residual would be minus 3. Yeah, so because it's 7 minus 10, so minus 3. And we can so keep going, right? So let's assume we have a one sample t-test. Now, again, as a reminder, one sample t-test. We test whether our data comes from a population with a certain mean. Yeah, so talked about that on Thursday. So we could test, for example, whether the mean exam anxiety. It's not a good example. Let's say the mean weight of Queen's College students is 120 pounds. Yeah, so that might be our hypothesis, right? And we could draw a sample of Queen's College students, so measure their weight. We would have a sample mean, and then we can run a one sample t-test to determine whether that sample mean is consistent with the hypothesis that the true underlying parameter is 120 pounds. So, and in this case, the residuals are just the differences between the observed values. Yeah, student A might weigh 130 pounds, so residual would be 10. So student B might weigh 180 pounds, so the difference is 60, so the residual. And this assumed population mean. For an independent samples t-test, where we're actually focusing on the difference between, basically whether we're focusing on the question whether two groups come from basically from the same population in terms of their means. So if two group means are identical or not, or show a certain difference or not, then so the residuals are the differences between the observed values from their corresponding group means. Yeah, so if we wanted to, for example, determine whether the weight is different between students from Queen's College, students from Hunter College, then our residuals would be the difference, the deviations of the students from the college, of the given college from their corresponding group means. Yeah. the reason why I am talking a lot about that is that it's very important to not get confused about the normality assumption. So you often may read something like that the data should be normally distributed for parametric tests, right? So the data, what is that? So I want you, that's why I'm basically, might sound a little bit like overly complicated to you, but that's why I'm insisting so much on this and this point that the residual should be normally distributed. So I don't even want to start with telling you that the data should be normally distributed. In many cases, it's the same, yeah, as for example, in a one sample t-test. So a normal distribution of the residuals is the same as a normal distribution of the data. In a two sample t-test, the normal distribution of the residuals is the same as a normal distribution of the data within each group. So I want you from the beginning to focus on this idea of residuals because it's much less confusing. You're much less likely to make a mistake when you're testing the assumptions. So, right, don't read it that way. And if you read something like that, so the data should be normal, always translate that into the residuals. So it should be, or the errors should be normally distributed. And a good example is the independent samples t-test, right? So where you compare the group means for two groups. So actually, so just to basically to show you how little sense it makes to assume that the data as such are normally distributed, right? If there is an actual difference between between the two groups. So yeah, if they're, for example, if I would compare men and so males and females, so men and women in terms of their mean weight, so then I of course, yeah, so there's almost definitely, so there will be a difference. And if we merge these two groups, if I look at the combined sample of men and women, then I actually would expect a bimodal distribution. Yeah, so where I have one maximum. So one peak for women, it's probably more the lower one, and then one for men. Basically, if you put the two populations together. So therefore, it's actually always a better idea, always a good idea to look at the distribution of the residuals. Yeah. And so also that is a common mistake, and and normally I go over the t-test as well, but I stopped doing that because I rather want to, I feel you have heard so much about t-test. I really don't want to do that anymore, but I still, so I feel that not everything is always fully understood. So if we have a pair t-test, so a pair t-test where we have dependent measures. So yeah, like this pre-post measurement, right? So we want to see whether there's a reduction in symptoms pre and post, like a certain intervention, taking a certain drug or doing some therapy. So then basically what we are focusing on are differences. So a dependent sample t-test is nothing but a one sample t-test on the differences. So that's what has to be normally distributed here are the differences. Does not matter what's the actual variables. The pre-test data don't have to be normally distributed, and the post-test data don't have to be normally distributed. What has to be normally distributed is a difference. Yeah, and then the deviations of each individual difference score, yeah, so the pre-post difference for participant 1, pre-post difference participant 2 from the mean difference. These are the residuals. Yeah. To be running a t-test over the pre-post differences, over the difference scores, and then the deviations of each individual participant from this mean difference. These are our residuals. Okay, think about it. As I said, sounds overly complicated, but it's really important to wrap your mind around that, so that you understand what is actually the assumption, what are we testing here. Okay, so when does the assumption of normality matter? So I said that before, mostly in small samples, So if you have large enough samples, we don't need to worry about it in most cases. Yeah, so the central limit theorem, thank God, yeah, allows us to forget about this assumption in large enough samples. But, so what the exact sample size is, that depends on many factors. Yeah, it depends on specific test statistic, on the parameter that we're interested in, whether it's the mean or some other parameter. It depends on the characteristics of the sampling distribution, so heavily skewed or heavy tailed this distribution is. So, and if it's like, yeah, if for example, if we have a high kurtosis, if we have very fat tailed, so if we have many extreme values or more extreme values in a distribution than in a normal distribution, we need larger n's. Yeah, if we have a heavily skewed distribution, we need larger n's. Again, 30, that is just a rule of the thumb. Yeah, so normally you can keep that in mind as a general guideline. If our sample size is fairly large or large enough, I would actually, I mean, always depends on what it looks like, but I would rather say if you think like 50 is probably a safer estimate, especially if you have like larger deviations from normality, then typically outliers are more to worry about than so the normality. Okay, so that is just something as a fun aspect. So a second reason to care about normality, right? So just find that entertaining and also interesting to think about. So if you have random and independent observations, which are, again, so the assumption and the prerequisite for any statistical test. And if your observations come from a normal distribution, so then the sample mean and the sample variance are always independent. However, yeah, so or what does it mean? Yeah, so that is not the case if you draw from a normal, for example, from a heavily skewed distribution. So what does it mean, right? So what does it mean sample mean and sample variance are independent? And it means, or it implies that how much you are wrong or how much you err when you estimate the mean from your sample does not influence, is unrelated to how much you err when estimating the variance. So they are independent from each other, right? You can make a big error regarding the mean, but a small error regarding your variance and vice versa, right? So they're absolutely unrelated. However, if you sample from a non-normally distributed population, the two errors are related. Yeah, so that means if you overestimate the mean, then so you can either over or underestimate the variance. Yeah, so you can have a positive or negative correlation, and the math is really, really difficult in that case. Oh, that's just a fun fact, so to keep in mind. And we were mentioning that just a few minutes ago, that the second assumption that parametric tests make is very frequently called the homogeneity of variance or the homoscedasticity. Yeah, so homogeneity of variance, so it's often used when we are talking about so designs or tests where, like, designs where we have group data. And like when we have a categorical predictor, so like when we run an analysis of variance, for example, to compare different group means or combinations, right, of certain factor levels, or if we have a t-test, right, so where we compare only two groups. So then it's often called homogeneity of variance, where if we have like, so if we look at ungrouped data, like in a regression analysis, so then it's most commonly referred to as homoscedasticity, but it's the same assumption. So, yeah, so for, mentioned that earlier, for a t-test that compares two independent groups, so each group should have the same variance. So each group in itself, so or a dependent variable or a variable of interest should have the same variance within both of these groups. And that equates to the assumption that the residuals should have the same variance across all levels of all values of the predictor. Yeah, and a good approach to assess this assumption, to test this assumption, is to plot our residuals versus the predicted values. And then, so these residuals should have approximately the same spread across all predicted values. So that makes most sense, right? I mean, of course, when we have a continuous predictor and a continuous dependent variable. So the opposite, by the way, of homoscedasticity is called heteroscedasticity. So the homogeneity of variance assumption is central to linear regression models. It's central to the F-test. Yeah? So when we're running an analysis of variance, to t-test, and many others. And so we can make, so if we violate this assumption, so we make two, we may have two problems. So the first problem concerns the parameter estimates themselves, and the second problem relates to the inferences, so into any significance testing that we are doing based on these estimates. So the parameter estimates themselves, so when we use don't worry about the least squares, so hopefully we will get a chance to talk about that later in the semester about the different estimation methods. But so the parameter estimates themselves, so when the homogeneity of variance assumption is violated, are unbiased, so that is good, but they're not very efficient. No, it's not good, right? But at least they're unbiased, so that's good. We're not making like a systematic error here. We just have more variability. Yeah, so they are basically more. So on average, we have stronger. So we have a larger deviation. So they're more spread out, right? Our distribution is wider. However, when it comes to null hypothesis significance testing, so then we have a bias. So then because the standard error of our parameter estimate is biased. So that is where the real trouble begins. So that means the results of our significance tests are no longer valid. Yeah, so the parameter estimates themselves are just a little bit more uncertain, so less precise, but our significance testing is biased. So it's not valid, it's invalid. So that's not good. Okay, so let's just summarize. So what we have talked about so far. So we have talked about parametric statistics and how they make certain assumptions about the probability distribution of the variables of interest. Well, non-parametric tests make no such assumptions. And so the two of the most frequent assumptions of parametric tests are the normal distribution of residuals. Yeah, residuals are just also called errors. And it's a difference between the observations or observed values, and so the value that is predicted by the model. Yeah, so again, model is a little bit abstract. We will, when we actually talk about our different statistical tests, it will hopefully become a little bit clearer. So remember, right, so we're talking about this t-test and how the mean is a model, right? That's a model prediction, and then the deviations of the individual observations from the mean versus residuals. And then for a regression model, if you remember that, recall that from last year, hopefully from last semester, right? So if your regression line, so the residuals as a deviation of the individual observations from the regression line. And the second assumption that is often made is a homogeneity of variance, and that just means that the residuals should have the same variance across all levels, across all values of the predictor. And in addition, parametric tests are very sensitive to outliers, always a reason to worry about. All statistical tests, parametric and non-parametric tests, assume that data are randomly selected, right? So we have random sampling, and that our observations are independent from each other. Or again, so you can think about it in terms of the error terms, also less confusing, same as for so the normal distribution assumption. Yeah, or error terms are independent. So our normality and homoscedasticity assumption can be checked using graphical methods, plots and numerical methods, statistical tests, and the random sampling and independence of observation have to be ensured by proper sampling techniques and study design. If the assumptions of parametric tests are violated, which is the most pressing concern in small samples, or if we have extreme outliers, then we need to use either non-parametric tests, or we have to use other statistical tests that are also called robust tests for those data, right? So that that violates the assumptions. I mean, we'll talk about that, for example, when we talk about our statistical tests. For example, we will touch on robust regression and how that differs from our classic ordinary all least squares regression. Okay, so after talking about what are the assumptions, so how can we actually measure, can we assess so these assumptions? And again, so for the normality assumption, so we can rely on the central limit theorem, and we know that with large enough samples, we don't have sleepless nights because of the normality assumption. So most importantly, we always want to look at at our data, of course. So we have certain ways for visual display to check our normality assumption. And the first one are called probability plots. So here we have QQ plots or PP plots. So that's a quantile plots or probability plots. I'll talk about that in a second. Or we can look at histograms where we are right, so just plots a frequency distribution of our data. And so in terms of the numerical methods, we can look at skewness and excess, skewness and kurtosis. Both we know are null in a normal distribution, and we can basically use the standard normal distributions, the Z distribution, to check whether our values significantly differ from 0 or not. And we can also use more formal tests. I mean, the Z test is also a formal test, but so we can, so most notably the Shapiro-Wilk test, also the Kolmogorov-Smirnov test, Anderson-Darling, so they're all doing the same thing. They test if data differ from a normal distribution. So they're significant if the data is non-normal, and they're non-significant if the data are normal. That is not 100% true the way I said it. So if they're significant, so that indicates the data are non-normal. If they're non-significant, we maintain or we keep the null hypothesis that the data are normal. Does not mean the data have to be normal, right? Problem with with all these formal statistical tests is that they depend on the sample size. That means for a large enough sample size, even minor deviations from the normal distribution that are really not relevant are significant, and for small sample sizes, even major deviations that are very impactful remain undetected. So that is always, you have to take that with a grain of salt. So that's why it's actually a good rule of the thumb to look at the graphical displays for large samples and just check, right, where outliers are a bigger concern anyway. And then for smaller samples, I would probably rather use robust methods or a non-parametric test, to be honest, especially if there's reason for doubt. Okay, so what do our visual displays or graphs for testing the normality assumption look like? So we typically want to plot the histogram with a normal curve superimposed on it. So right, so it's just a frequency distribution, and then we basically put the normal curve here for this distribution as a comparison on top of it. However, the problem with the histogram is it always depends, so the appearance depends on how many bins we are using, so what our bin width is. So it can change the impression considerably, so that we get the idea that we get how the distribution looks like. And sometimes it might therefore be better to plot a kernel density plot. Again, so as a reminder, kernel density plot is similar to a histogram, but it's smoothed into a curve. It's just an estimate of the density probability function for our data, right? It's an estimate from the sample, what the density looks like. And so it basically gets rid of this problem with choosing the right bin size. So that's why it can be more informative in some cases or in many cases. Another actually very important way, and I would say the most commonly used way to spot deviations from the normality assumption are the so-called QQ or quantile plots. So, as I said, so the QQ stands for quantiles. So we are plotting quantiles against quantiles, and what quantiles are we plotting against each other? So we do nothing but to and again, so the axis can be changed, right? So that is makes it sometimes a little bit more controversial how to look at it. So we plot our the quantiles for our observed data against the corresponding quantiles of the normal distribution, right? And so as I said, so we will talk about it in more detail in a minute, but so just for now, so these data points should lie approximately on a straight line. So if they are not on a straight line like here, if that looks more like S-shaped, then so this indicates some deviation from normality. Okay, and then so these QQ plots are also a little bit hard to wrap your head around what is displayed in here. So that's why I would like to guide you step by step through them because it's really important to understand. So what are we doing when we are plotting these? I mean, software is doing for us. But so first of all, we take our sample data and we sort the values by their value. So basically in ascending order, right? So we start with the smallest values and we end with the largest values. And then we determine the quantiles or percentiles for our data. Yeah. So let's assume we have, to make it easy, right? So we have 100 data points. Yeah. So then the first data point, so our smallest data point, corresponds to the first percentile. So then we look up in our normal distribution function, what is the quantile? So what is a corresponding quantile for the first percentile for a standard normal distribution? Yeah, so what is the corresponding Z value? And how can we do that? Everybody should know that. In R, what function would we use if we want to know for the first percentile, what is a corresponding Z value? What function would we use?
If it's Z value, then we would use Q norm, because these are Q plots, right? Or is it P norm? Yeah, Q norm. Yeah,
exactly. So we would say Q norm of 0.01, right? So that's a Q norm, that is our Z value for the first percentile, right? And it should be roughly like minus 2 point, I don't know what, 2 point something. Yeah, so that means over 2 standard deviations below the mean, right? Below 0. And that's what we're doing, right? So that we're plotting. We are checking what is the sorry, and then we're plotting that against the actual Z value for that is calculated based on our sample, right? So our observed Z values basically. So we Z transform our data in the sample, and for each value we are plotting its actual Z values. That means how much it deviates from the sample mean in terms of how many standard deviations that it is away from the sample mean. And we compare that basically. So we plot that against what a value that has this percentile. Yeah. So in a standard normal distribution, how far away would that value be from the sample mean? Yeah. So for if we have the 100 data points, so right, for our smallest value in the standard normal distribution, it should be approximately 2.5 standard deviations away from the mean, right? But in our sample, it might be further away from the mean because it has a negative skew, right? Or it might be closer to the mean because it has, or distribution is actually has fewer extreme values. It has smaller kurtosis than the standard normal distribution, right? And that's what causes these deviations of from the straight line here. right? If we have the non-correspondence between what z-value would be expected if that data would come from a normal distribution compared to what z-value we actually find based on our sample data. All right, so it's relatively late, but so still I would like to, I never get through my stuff, I'm babbling too much, but I wanted to show you, despite the fact that we will run out of time, so this video, because I really want you to understand QQ plots. They're very important, and from my experience, previous semesters, students never fully understand what is shown in the QQ plots. That's an excellent video, I hope it will help.
Let's look at normal quantile plots, which can help answer the question, is a set of observations approximately normally distributed? If a set of observations is approximately normally distributed, a normal quantile plot of the observations will result in an approximately straight line. We sometimes call a quantile plot a QQ plot for short. Here's an example of a normal quantile plot for a sample of size 9 from a normally distributed population. These points fall in a pretty straight line. We sometimes draw a line in for a little perspective. More on that line a little bit later. Assessing normality is important, as many statistical inference procedures assume we are sampling from a normally distributed population. And so we are going to want to investigate that assumption to see if it's reasonable. Now let's work through some of the details in how a normal quantile plot is constructed. Does the following sample come from a normally distributed population? First, we're going to order the data from smallest to largest, and then we're going to plot these values against the appropriate quantiles from the standard normal distribution. Let's look at that in a little more detail. Here we have the standard normal probability density function truncated at -3 and 3. And down here, we have our 9 sample values. And what we're going to do is we're going to place 9 values down here for a standard normal random variable, such that the distribution is split up into n+1 or 10 equal areas. So we're going to split this distribution up into 10 equal areas because we're placing 9 values down here, and so the distribution is going to be split up into 10 areas.
So just as a quick comment, so the 10 equal areas means that the area under the curve is the same size. So the probability is the same, yeah? It does not mean they're equidistant on the x-axis. It means that actually for each portion here, the area under the curve, so that means the probability is the same.
Areas. And that looks like this. Might be a little hard to tell, but this value says 0.1. All of these areas are 0.1 because there were 10 areas and the area under the entire curve is 1, of course. And now we're going to find the values of a standard normal random variable that make that happen. So we could go to computer software or possibly a standard normal table. We would find this first value rounded to 2 decimal places is -1.28. Now let's do that for a few more of them. I'd put all 9 of those values in, but that would look a little messy here, so I just put in 5 of them. Now, if we were sampling 9 values from a standard normal distribution, a little loosely speaking, we would expect the smallest value to be around -1.28. And this one's not written there, but it's -0.84 to 2 decimal places. We would expect the second smallest value to be around -0.84. And the third smallest value to be about -0.52, and so on and so forth, up to the largest value around 1.28. So what we're going to do is we're going to plot the smallest value in our sample of size 9 against what we would expect to get as the smallest value in a sample of size 9 from the standard normal distribution, and the second smallest value against what we would expect to get as the second smallest value in a sample of the same size from the standard normal distribution, all the way up to plotting our largest value in the sample against what we would expect to get for our largest value from the standard normal distribution of the same sample size. And if our data is approximately normally distributed, that should result in an approximately straight line. Now, we could have picked a different normal distribution. We didn't have to pick the standard normal distribution. Some things would change in terms of the scaling, but overall the general idea would be the same if we were to use any normal distribution, but we typically simply use the standard normal distribution. And if we were to plot that out, here's what we get. I'm labeling the y-axis here as the sample quantiles, and those are simply our observed values in the sample. And on the x-axis, I've got the theoretical quantiles. And loosely speaking, those are the values we'd expect to get in a sample of this size from the standard normal distribution. And the resulting plot is a pretty darn straight line. So this would say that that sample data is approximately normally distributed. And just in case it's not clear what these points represent, this value here is the smallest value observed in our sample of 3.89, and it was plotted against the corresponding value from the standard normal curve of minus 1.28, and similarly for the rest of them. What did we just do here? We plotted the ith ordered value, sometimes called the ith order statistic, against the I over n plus 1th quantile of the standard normal distribution. So for example, when I was 1, we took the smallest value in our sample and we plotted that against 1 over, we had a sample of size 9, so 9 plus 1 or 0.1, and the 0.1th quantile of the standard normal distribution. Or in other words, if we have 0.1 to the left, this value here that yields 0.1 to the left is the 0.1th quantile of the standard normal curve, also called the 10th percentile, if we wanted to call it that. And we use that method for all of our ordered data values. Instead of using I over n plus 1, there's a variety of other possibilities, such as I minus a half over n, or more generally, I minus a over n plus 1 minus 2a, where a is some number between 0 and a half. This, if we think about this is the same as the general method with a of a half, and what we had up here is the same as the general formulation with a of 0. And different values of a have been proposed as well. But let's not get too bogged down in that. What we are simply trying to do is come up with a method that approximates what we would expect to get if we were sampling from the standard normal distribution. Now let's look at a few things we might see in practice. Usually in practice, of course, we use statistical software to actually do the plotting. And here I'm going to use the statistical software R. R's method differs slightly from what I described earlier, but overall the idea is the same. In this first plot, I'm sampling 50 observations from a normally distributed population. And we get a normal quantile plot here that results in a pretty darn straight line. This line is drawn in for a little perspective. And R draws in a line that joins the first and third quartiles. But there are other lines we could draw in, but that's R's method. So overall, our points form a pretty darn straight line, which shouldn't be too surprising because we are indeed sampling from a normally distributed population. But let's see a couple of instances where we're not sampling from a normally distributed population. Here I'm drawing a random sample of 50 observations from a uniform distribution. And if I was to superimpose a normal curve over this, say, we'd see that the uniform distribution is truncated tails. So we're not going to get extreme values in this distribution. How that manifests itself in the normal quantile plot is that these values, corresponding to the large values in our sample, are not as far out in the right tail as would be expected if we were sampling from a normally distributed population. And the smallest values in our sample are not as far out in the left tail as would be expected if we were sampling from a normally distributed population. So we see this curvature here. One thing to keep in mind is that there are different plotting methods, and sometimes people switch the axes here. and have the theoretical quantiles on the y-axis and the sample quantiles on the x-axis. In some ways, it doesn't really matter. We're still going to see the curvature, but we just have to be careful in our interpretation of what that means. Here I'm drawing 50 observations from a distribution that is strongly right skewed. And what we see in our normal quantile-quantile plot is that the largest values in our sample are much larger than would be expected if we were sampling from a normally distributed population, because we've got this heavy right tail here. But in the left tail, the dots creep above the line here, indicating that the smallest values in our sample are not as extreme as would be expected under normality. And we can see that up here in our PDF as it ends pretty quickly here at 0. Here I'm drawing 50 observations from a heavy-tailed distribution, a distribution that has greater area in the tails than the standard normal distribution, so we're going to expect to get more extreme values. And we see that in our normal quantile-quantile plot. These values in the right tail of our distribution, the largest values, are even larger than would be expected under normality. And these values in the left tail of the distribution, our smallest sample values, are even more extreme than would be expected under normality as well. Properly interpreting normal quantile-quantile plots can be a little tricky without some experience. But fortunately, we can get some experience pretty quickly using simulation. What I plotted out here is the normal quantile-quantile plot for a sample of size 50 from the standard normal distribution. And this results in a pretty darn straight line. But sometimes, of course, natural variability will lead to us seeing some curvature or a major outlier or something along those lines. So I'm going to replicate this or carry this out 20 times and see what these different normal quantile-quantile plots look like when we are in fact sampling from a normally distributed population. When the sample size is a little bit smaller, the variability can be a bit more extreme. So let's see what it looks like for a sample of size 10. This is the normal quantile-quantile plot for a sample of size 10 from a normally distributed population. Let's do this 20 times and see what the variability is like. So that's our introduction to normal quantile-quantile plots. And we'll be using this method to investigate the normality assumption.
Okay, so that was hopefully a pretty comprehensive overview. And so the difference was he's actually not showing the standardized scores, so the standardized quantiles on the y-axis, which is typically done, but it does not matter, right? So how you scale it. So yeah, very important. And as he said, so it requires some practice to fully understand it and to get used to it. It's very important. It's really very, very important. And it's very important to me that you understand what is shown in the plot and what it means if the scores deviate in one direction or the other, right? So as he explained for the skewed distributions, for the heavy tail distributions, so what you would expect. Okay, very important. So there's, so this is here an applet that also shows you how the QQ plots are generated from distributions, also very helpful and basically getting a better idea of how it works. And so then there's also like a brother to the QQ plot. That's a PP plot, or probability plot. And it's very similar in a way. So, but it does not plot the quantiles of like the, your empirical quantiles, rather the theoretical normal quantiles against each other, but the cumulative probability. Yeah, so it plots a cumulative probability of standardized data against the standard normal cumulative probability. So, and you're doing basically a very similar thing, so that you do for the QQ plots. So you first bring all your data points in a rank order, right? So it's an ascending order. and then you plot on the y-axis just your empirical cumulative density. So that means you just basically plot for each value. So how likely it is that this basically say that. So what is a percentile for this value in your sample, right? So and that is on your y-axis, so from 0 to 100, right? So again, if we take this easy case where you have 100 values, so your first value would be obviously so 0.01, so your first percentile, second value would be second percentile, third value would be third percentile, etc., 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 right? So and then on the x-axis here, so you first normalize the data, so you do a z transformation, and then so your empirical data, right? So you z transform the data, and then for these z values, you calculate the cumulative probability. Yeah, so basically, if your first value in your sample, let's say it corresponds to a z-value of minus 3.5, right? So so the corresponding z-value is minus 3.5. So then you would say, what is the cumulative probability in a standard normal distribution of minus 3.5? And that is pretty low, right? So that is lower than the first percentile, right? Which would indicate that this is a more extreme data point that we might expect of a sample from a normal distribution. So same idea, just a slightly different display. And the advantage of the major advantage of so in most cases we use a QQ plot. But an advantage of the PP plot is that the cumulative density actually changes most in the center of the distribution. So that's why a PP plot is more sensitive to deviations from normality that are apparent in the center, right? So around the mean of the distribution. So whereas the QQ plots are more sensitive to deviations in the tails. But it depends on. So I said, in most cases you use a QQ plot, quantile plot. All right. So I mentioned that earlier. So we can check normality also with statistical tests. And so one prominent test is based on so two components of normality. So these are skewness, so the symmetry of our distribution, and the kurtosis or excess, so means the heavy-tailedness or general tailedness of our distribution. And both are 0 for normal distribution, right? So just a reminder, kurtosis actually is 3 for normal distribution, but most statistics programs so convert it into excess, which is 0 for a normal distribution. So it's also the case that the sampling distributions for skewness and excess are approximately normal. That's a good thing, right? Because now we can use the standard normal distribution to determine the probability of obtaining a certain value for our skewness or for our excess, and basically determine whether any deviations that we get for our sample from any deviations of our skewness and excess from 0 are, so whether they are an unlikely event or a relatively likely event under this assumption that the data are actually normally distributed. So what we do is we just subtract the mean, which is 0 in this case, right? So the mean parameter, so 0 for kurtosis, 0 for skewness, and then we divide by the standard error for kurtosis and skewness, and then we just compare to the standard normal distribution. So this is an example here from just some data set where so there were 2 variables. One was exam anxiety and the other one was test performance. And so let's assume that so for exam performance, we observed a value of skewness, which is minus 3.73, so which indicates a little bit, has a left, so like a negative skew, right? So left skew, so the tail is longer. So the lower tail of the distribution is longer, right? So we have more extreme outliers in the left tail. And so the standard error that the statistic program spits out, I mean, it's also not hard to calculate, was 0.238. So, and then if we divide these two values, we get minus 0.56, so which is within normal limits, right? So that's a not too improbable value if we would actually sample from a normal distribution, from a normal population. You do the same for the kurtosis, which is here also a negative, right? So it's actually it's a lower kurtosis than the normal distribution. We divide by the standard error and get minus 1.81 again, right? So this is within the what we can consider relatively plausible under the assumption that we sample from a normal distribution, right? So for the other variable, the exam anxiety, so actually the observed skewness is -2. And then the standard error is 0.238, so the same as before. And so here we get the value of minus 8.45. Yeah, so that is 8 standard deviations below the mean of 0. Yeah, so that is very unlikely, right? So this is probably not from a normal distribution. And same for kurtosis, which here is much higher, right? So the kurtosis is 5, so it's much higher than for a normal distribution. Standard error is relatively low, so we get a value of 11. So that means this kurtosis is basically, so it's 5 times, so 5 standard deviations away from the mean of our sampling distribution. So highly unlikely. Yeah. So, and if you use that method, so for small samples, use conventional but so conservative alpha. So it means 0.01 or 0.001. All right. So you can also use so there are diverse statistical tests to test deviations from the normality assumptions. So one is the Shapiro-Wilk test. And that is basically, it just compares the scores in your sample to a normally distributed set of scores with the same mean and the same standard deviation. And then again, if those tests are significant, so it indicates that your data does not come from a normal distribution. If it's non-significant, you can keep the null hypothesis that it comes from the normal distribution. Problem, I mentioned that again, is that it depends on the sample size. If your sample is just large enough, even so the smallest deviation from normality, even it's absolutely irrelevant, of no practical relevance, will be significant, so rather inspect the shape of the distribution then. And you know for small sample, for large samples, the normality assumption is not that important anyway. I just wanted to mention that very briefly. So many statistical tests actually assume multivariate normality, especially the multivariate statistical methods. So, and multivariate normality means that each variable in your data set in itself is normally distributed, and all linear combinations of the variables are normally distributed as well. Yeah, so it's very hard to test actually, and typically we check whether the residuals of our model are normally distributed and leave it there, right? So, and that is, it's an okay thing to do. Just want to mention that here we will talk about it in more detail when we are discussing multiple regression. Okay, so what can we do to check for homoscedasticity? So again, reminder, right? So homoscedasticity, homogeneity of variance, means that basically the variance of our error terms of our residuals is the same, it's constant across all levels of our predictor. Right, so here we have so in a data set where I'm actually not sure, so it's from the Andy Field, so that he always has a textbook, he always has funny examples. So that is apparently ear ringing, so that's our dependent variable, and then it's in different cities here, right? So in this case, we would have a categorical predictor, right? So the different towns, and these are our data points. And you can see, right, so the data should, so basically, so they should randomly scatter around the predicted values. So that is the assumption that the distribution of the errors of the residuals is normal, right? So there's a mean of 0, and then the spread should be approximately the same. Yeah, so the standard deviation for this distribution of the residuals around the, right, so around the predicted values, that should be the same for all these towns, for all values of the predictor. And here you have an example where this is given, right? So here's the homoscedasticity assumption most likely met. Here you see an example for where so the variability is much lower for these first two cities or towns, and then you have much larger standard deviation, so of the residual, so much larger variability for the for Cardiff and Dublin, et cetera, et cetera. So that would be heteroscedasticity here, right? So it's also shown in the in these displays here in these graphs. Yeah, so these are basically so when you plot the residuals or predicted values against the or residuals against predicted values, or here's a predictor against the so the observed data, then there should be two things, right? So you should have a normal distribution and with a mean of 0, that is your normality assumption, and the standard deviation should be the same, and that is your homoscedasticity assumption. So they both are evident in the same plot. All right, so and here you see another example, right? In this case, you have the fitted values or the predicted values against the residuals, which is a more common way of displaying so the same thing. And here you see another case for heteroscedasticity. That means for larger predicted values, you have a much larger variance of the residuals than for the smaller predicted values, right? So a clear case of heteroscedasticity. So in addition to these residual plots, which we will talk about more when we are talking about regression, you also have statistical tests. So one is Levene's test, which is used when your test of the variance of different groups are the same, like for example, in the independent samples t-test. You have the variance ratio test, same with 2 or more groups. And there are many more. So R has a plethora of like different test methods, and we will cover them when we talk about the different tests. And notice it's just again as a an illustration of the homoscedasticity assumption, right? So if you have like two populations that we are comparing with each other, for example, depressed versus non-depressed, right? So two groups, then we want the variance of the of our dependent variable to be the same as the two groups, right? So we don't want it to be different. And again, similar to the tests for normality, if we have a significant result, so that indicates that our variances are unequal. All right, so let me just quickly summarize, and then I think we'll stop for today and cover the rest tomorrow. So correlation is actually not quite as much, so I'm hopeful that I might be able to get done tomorrow. All right, so right, so one of the two most common assumptions of parametric tests, so the normality of the residuals, can be tested using both graphical or numerical methods. The graphical displays, so one option for graphical displays are the so-called probability plots. So we are distinguishing between the QQ plot, the quantile plot, and the PP plot. So, and in both cases, deviations from a straight line indicate issues with either skewness or kurtosis, right? So that we have more or less extreme values than we would assume for a normal distribution, or we have, yes, or the data is skewed in a certain direction, so either to smaller or larger values. Yeah. And as a reminder, the quantile plot shows the standard data quantiles against the standard normal quantiles. Basically, it compares the so your observed, your empirical quantiles against what you would expect if you would draw a sample from a normal distribution. So, and if the data comes from a normal distribution, they should roughly correspond to what you can expect from a sample of that size that comes from a normal distribution. So it should be roughly on a straight line. If they are more extreme, right? So then you would expect from a normal distribution or less extreme, then this indicates so that you have a deviation of normality. And so PP plots are very similar. So they simply, the difference is they don't plot so the quantiles, but they plot the empirical cumulative probability against the standard normal cumulative probability. And just as a side note, so we are talking about that in the context of the normal distribution. You can create QQ plots and PP plots for any theoretical distribution. Yeah, you could test whether it comes from a T distribution or from chi-squared or whatever, right? So it can be any theoretical distribution, right? It doesn't have to be a normal distribution. We are just checking here whether, right? So what we wanted to check here was whether it's normally distributed or not. And we can also create a histogram with a superimposed normal distribution. And just a reminder, histograms have this ambiguity because of the bin width, or depending on how we choose the bin width, the distribution can look quite different. So that's why it's often helpful to also plot a kernel density plot where we have a smooth curve that is the estimated density function for density distribution for our variable of interest, and avoids that problem. There are a number of numerical methods, so it means statistical tests to test the normality assumption, right? So in all cases, significant results indicate that the data are not normal. And so we have, we can use a z-test to check whether skewness and excess are significantly different from 0. Or we can use other tests, right, like the Shapiro-Wilk test to compare our observed scores to a normally distributed set of scores with the same mean and the same standard deviation. And so just a reminder, multivariate normality is hard to test. So that means that not only, so if we have more than 2 variables, like a multiple regression, for example, then multivariate normality is required. And it's not only that each variable in itself is normally distributed, but so that their bivariate or like multivariate distribution is normal as well. And so we typically are satisfied with showing that the residuals are normally distributed because it's really hard to test. Okay, so I would say let's stop here and let's talk about data screening tomorrow. And yeah, and I will post the so a hint on how to transform the data set for the plots for today's assignment. All right. Okay, any comments, questions, anything else that I need to do before tomorrow? Was this assignment or?
I just wanted to say.
So go ahead.
Would you post the updated slides?
You mean for today?
Yeah.
Oh yeah, thanks for the reminder. Yeah, I changed them a little bit in comparison to what I posted yesterday. So yeah, I will do that. I will take them down, the other slides, and post the new ones today.
Yeah, I would really appreciate the help for 5B because it was a real struggle. I think like I still wasn't able to figure out how to format that for R.
All right. So yeah, I will do that. So hopefully that will help. I mean, if you still have issues, then let me know. I will do it right away.
Thank you.
All right. Okay. Then I'll see you tomorrow. And we will talk about data screening and correlation. Yeah. Then have a good night.
Have a good night.
Bye. Have a good night.
Bye.
Good night. Thank you.
Bye.
Alrighty, I will just, so let me just stop the recording.